take a look at the sketch and make solid as possible, and then we'll take a spin with our little car and drive it around the room. So here's the sketch I've come up with in order to control my little car with a joystick. Now, as with all the other sketches, you can find these on dronebotworkshop.com along with a complete explanation of each sketch. But I'm going to go over this one with you right now. Now, we start off the same as we have with our other sketch. We define a number of integers, and these are for the inputs and the enable lines for the L298N. Then we've got the analog inputs of the Arduino, which I mapped out to joy verse and joy chords for the vertical and horizontal potentiometer in the joystick. As with our last sketch, we define a couple of integers to represent the motor speed for each motor, and we initialize them at 0. We've also got a couple of new values here for the vertical and horizontal positions of the joystick, and they're initialized at 512. Now remember that the analog to digital converter in the Arduino will convert the input voltage to values between 0 and 1023, so 512 is pretty well in the middle of the range. Then in the setup, we go and initialize our pins as outputs as we did before, and we'll also start our motors off, both disabled with enable A being low and enable B being low, and also set the motor to spin in a forward direction. Then we go into the loop. Now we're going to get the joystick positions and put them into the values that we defined for joystick positions using an analog read command, just like we did with the potentiometers in the last sketch. Now remember, the vertical joystick is the one which determines whether we're going forwards or backwards. If we push it all the way up, we want to go forwards. If we pull it all the way back, we want to go backwards. Also, the more we push it up or the more that we pull it down, the faster we want to go. So we're representing both speed and direction with this joystick. Now, the vertical position will be above a value of 512 if we want to move forward, and it will be below 512 if we want to go backwards. However, we have to consider that most joysticks are not perfect, and that the variable resistors and potentiometers inside them have a little bit of a tolerance. So I've allowed about 10%, and I've decided that any value above 564 means that we want to go forward, where a value of below 460 determines we're going backwards. So in the first case here, I evaluate for values below 460. We want to go backwards. We'll set the motor directions backwards, and then we'll go and determine the motor speed. Now, in this case, as we pull the joystick down, the numbers we're reading on the analog input are going to get lower and lower, yet we want our motor to go faster and faster. So we need to do a bit of math. So I take the value, and I subtract 460 from it. That's going to give me a negative number. And so what I need to do is multiply that by -1 in order to make it positive. Then after that, I use the map command, as we've seen before, to map the values between 0 and 460 to values between 0 and 255, so I can drive my motors with pulse width modulation. Now, in the case where the vertical potentiometer is reading above 564, we are going forward. So again, we'll set our motor direction to forward, and we'll determine the motor speed with a map command. We don't need to do the fancy math we did before, because as we push the joystick forward, the values are going to go up and up. So we'll just map the values of 564 to 1023 to values between 0 and 255. If it doesn't evaluate to either of the previous two conditions, then the motor stops, and we'll set the motor speeds to 0. Now we'll do the steering, and we do that with the horizontal potentiometer. Again, we use the criteria of below 460 or above 564. If it's below 460, we do basically the same thing we did before. We do the mathematics and convert it to a positive number. And then we'll map that position to a value between 0 and 255. Now, we do a little bit of math after this, because remember, when we want to turn left, what we want to do is spin the right motor faster and spin the left motor slower. So motor number 1 is our left one, and motor number 2 is our right one. So on motor number 1, we actually minus this value from the current motor speed, which we determined earlier. On motor number 2, we add the value to it. So we make motor number 1 go slower and motor number 2 go faster. Now, this will likely produce a value in many cases that exceeds 255 or goes below 0. So we have a couple of if statements here. If the motor speed is below 0, then it's equal to 0. Whereas if the motor speed is above 255, then we'll equal it to 255. Now, if the horizontal is above 564, we want to turn right. And we basically do the same thing. We'll map the values, and then we do the same math to add and subtract them. Now, you'll notice that in this case, we are adding to motor speed number 1 and subtracting from number 2, because this time we want to turn right. Again, we make sure we don't exceed the values of 255 or 0. Finally, I have the same statement I've always had to prevent the motors from buzzing. If the motor speed is less than 8, then we'll just consider it to be 0. And last but not least, we use the analog write command to write to the enable lines of both the two motors to spin them at the correct speed. And then the loop just repeats itself as long as the Arduino is powered up, and we can drive our car around the room. So now it's time to give our little car a test drive. As you've noticed, I've put a very, very long wire between the car and the L298, and that's, of course, so I have a little bit of space to maneuver the vehicle. So I'm going to stick this down on the floor and see if I can drive as best as I can. I'm going to move the joystick forward, and our car moves forward. I move it backwards, the car moves backwards. I'm going to move a little off to the right, and move a little off to the left. And so I can steer the car, too. It's not that practical with this wire on it. But as you can see, it's actually a working little robot car. Okay, so that about does it. We learned quite a bit in this video, haven't we? We learned what a DC motor is, how it works, even a little bit about the history about DC motors. We learned how an H-bridge works, and how we can use the L298N H-bridge controller with an Arduino, even without an Arduino, to control a pair of motors. We've taken that knowledge and we've even built this cool little robot car that we can drive around the room with a joystick. So I think we've covered quite a bit. I hope you've enjoyed it. If you did enjoy it, please consider subscribing to the channel. And if you have any comments, please leave them below the video. If you need the code for any of these projects, visit DrumBotWorkshop.com, where you'll see a detailed article about everything we've covered, as well as all the sketches you'll need in order to recreate all of these experiments yourself. So thank you once again for joining me, and I hope to see you soon in the workshop. Take care. Today in the workshop, we're going to be assembling a small open-source robotics arm called the knee-arm. I'm going to take you step-by-step through the assembly of the knee-arm using the knee-arm kit for Arduino. It's a pretty easy device to put together, but watch out. I made a huge mistake at the beginning, one that you're not going to want to repeat when you build your own knee-arm. So stay tuned, and welcome to the workshop. Hey, welcome to the workshop and to the first video in our series of the knee-arm. Now, for those of you who aren't familiar with what a knee-arm is, it's an open-source robotics arm that was originally developed to teach school children about robotics. However, the knee-arm is a useful tool for any robotics enthusiast. The knee-arm is open-source, and therefore all the plans for the knee-arm are available freely online. So if you have a 3D printer or the ability to cut plexiglass, you can put together all the mechanical parts of the knee-arm on your own. However, for most of us who don't have those facilities or who want to save a little bit of time, you can buy a knee-arm kit, and that's what we're going to do in this video. I've just received this knee-arm kit. We're going to open up the box and see what's inside it and start assembling our knee-arm. So let's begin by opening up the knee-arm kit and seeing what's included. Now, I've purchased the knee-arm kit without the controller, as I intend to use my own Arduino to control this. So if you purchase the knee-arm with a controller, you'll likely get a bigger box that also includes the controller device. Now, my knee-arm kit says that it was confidently packed by John, so I'm sure John did a great job of packing this. Let's see what he packed for us. Okay, we open it up, and we learn that the instructions are available at learn.mine.co.uk, and many thanks to Ben Gray, Ben Kurt, and John Sherwood. So that might be the John who packed my kit. So thank you very much, John. A little brochure for the knee-arm and another product called the knee robot. And then the meat and potatoes. Here we have a package of plexiglass parts that have all been cut for us. There seem to be 4 sheets with several parts on them. We'll put those aside for now. Here. Now we've got 4 servo motors. These are MT90S servo motors. They're the Metal Gear version of the ST90. They use just basically 4 packs of them. It's nice to see they use the Metal Gear servo motors in this. Here's an extension for one of the servos. I guess one of the servos doesn't actually reach down to the controller, so this gives you an extra couple of inches for this servo wire. It's very handy. A tiny little knee-arm sticker, which I'm sure will come in very useful at some point. And the fixings pack with all the nuts and bolts that you're going to need to assemble our knee-arm. So here are the contents of the bag that contains the plexiglass components of the knee-arm. As you can see, it comes with 4 sheets of plexiglass, and each one has been cut out into a number of different parts. These components will, of course, be assembled in order to create our knee-arm. Now, this might look a bit complicated, but fortunately, the folks at knee-arm have provided a PDF document that should assist with assembly, and I'm going to be going over this step-by-step during this video. So here's the contents of the fixings pack that comes with the knee-arm kit. These are all the nuts and bolts required to assemble your knee-arm. I laid mine out on the Masters mixer, and I was given all of them, and indeed I was. They are as follows. These are the 3mm nuts. There's the 6mm screws, some 8mm screws, some 10mm, 12mm, and 20mm. These are all 3mm diameter screws. In addition to that, they've given me 4 feet for the base of the knee-arm, and an Allen key that can be used to assemble all of the screws. Now, in my case, I decided I'm going to use a screwdriver instead, so this is a 2.5mm hex driver that I'm going to use instead of the Allen key, although I very much appreciate they provided the Allen key. I'm also going to use this plastic parts box. I'm going to place all of the parts that I have here into the plastic box, and that way I can keep track of them, and they won't start rolling under the workbench, which inevitably they certainly will do. So here's one of the servo motors that's included with the knee-arm kit. There are 4 of them in total. They're standard MT90 servo motors, which are the Metal Gear versions of the ST90 that you're probably already familiar with. As with the ST90s, they come with a series of arms that can be attached to the motors. And in the instructions for assembling the knee-arm, they will show you which of these arms to use in which section. Now, the first step in constructing the knee-arm is to calibrate the servo motors. It's going to be you unlock the controller when you need seen some Arduinos do this, and they have instructions for that in the PDF manual that you can download from the Nearm site. I should mention there are a couple of small inaccuracies in that manual. First of all, the diagram for the motor hookup shows the motor colors as being yellow, black, and red. In actual fact, the wires on the servo motors I received were orange, brown, and red. This is very common for MC90 servo motors. They go as follows. The yellow wire they show is actually the orange wire. This is the pulse width modulation input to the motor. The black wire that they show is the ground wire, and that is the ground for the motor. And red is indeed correct as being red. That's the positive 5 volts that you apply to the stepper motors. Now, you'll need to apply 5 volts to an external supply. You can't use 5 volts from your Arduino because it simply does not have the current capability to drive force servo motors. So, otherwise, the diagram is correct in its hookup. We will hook the middle motor to line number 11 on the Arduino Uno. The left motor will go to digital output pin number 10, the right motor to output pin number 9, and the claw motor will go to output pin number 6. Now, you can use different pins, especially if you have another Arduino. It's just important to realize that the pins have to be capable of pulse width modulation. On the Arduino Uno, only 6 of the 14 digital outputs are capable of PWM. Once you've done that, there's a sketch that you can load into your Arduino to calibrate the motors. Again, there's a slight error in the PDF document. It simply leaves off the trailing curly bracket, which we usually have. They also give you a site that you can go to, the code vendor site, which has a copy of the sketch, and that's a lot easier to use. Just copy that and upload that to your Arduino. Once you hook that up, the motors will go to a predetermined position. And at this point, we're going to mark our motors with a marker pen so that we can install a couple of these arms on the motor and have them in the correct position. This is very important because if you don't do this, your V-arm will not be calibrated when you first turn it on. Now that you've hooked the Arduino up to the motors and run the calibrate program, you need to mark the calibration points on the motors. You can do that with a permanent marker pen. I've already done a couple of them over here. I don't know if you can see that or not. I'll do these last two. You essentially look at the motor at this angle here with the wires coming out the left side, and you draw a line down here and across the shaft of the motor itself. And I'll repeat that for the last motor. These calibration marks will become useful when you're assembling the Nearm. After that, you're going to put the motor arms onto the motors, and there's a diagram that shows how they're done. So I'm going to do it starting with the middle motor, which in my case is the motor on the top. You'll take the long arm for the middle motor, and it's going to go at a 90-degree angle. Let's get it in there. There we go. And then you take the machine screw, and you'll need a small Phillips screwdriver. And you place that in there. Now the left motor uses the same arm, except it's installed at this angle, and again with the small machine screw. Be very careful that you don't cross-thread any of these. The right motor is done the same as the middle motor. And then finally the claw motor, which uses the shorter half arm, and it's installed. Make sure that the half arm is pointing away from the side with the wires. And again, of course, we'll use the small Phillips machine screw. There we go. Our motors are calibrated and the arms are installed. So now that we've done the calibration of the servo motors using the Arduino, it's time to actually build our Nearm. All we're going to need is a little Allen key that came with the Nearm schedule. I'm going to use a 2.5mm driver because I think it might be a little easier. Also, you'll need a small Phillips screwdriver for the servo motor screws and the Nearm instruction manual. So let's grab all of that. I'm going to head over to my other workbench and I'm going to start assembling my Nearm. The first step in assembling the Nearm is to take the middle servo motor and insert it into the servo collar. Note that there's a notch on the collar. This is the side that the wire of the servo motor goes through. So then take the servo collar and attach it to the pivot servo plate using 2 of the 8mm screws. Tighten both of the screws so that the motor is mounted firmly to the plate. However, don't over-tighten them because you'll risk cracking the plastic on the servo motor collar. The next step in assembling our Nearm is to attach the pivot servo plate to the Nearm base. You will do this using 4 20mm screws. Insert each of the screws into the hole in the base, and then thread a nut about halfway down each of the screws. Now attach the plate. Note the orientation with the servo motor wire going toward the center of the Nearm. You'll then thread each of the screws into the plate until it is flush with the top of the plate. Once you've done that, just hand thread each of the nuts down toward the Nearm. arm base. The resulting assembly should look like this. Next, we will take the left servo motor and insert it into the servo collar plate. Again, notice the orientation of the wire with the notch in the servo collar plate. We will then insert this into the left arm servo plate using 2 of the 8mm screws. As with the previous servo motor, tighten the screws but don't over-tighten them. Now we will attach the servo arm to the long servo arm extension. To do this, we'll use 2 of the small screws that come included with the servo motors. Take your self-tapping screws, which we'll use to hold the servo arm onto the servo arm extension. Tighten both of the screws. Now we'll take the servo arm extension and attach it to the left servo motor. Notice the angle that the extension is attached. You'll use the machine screw that came included with the servo motors to attach it. After hooking the arm extension to the servo motor, you may wish to recalibrate it using the same setup you used earlier. Make sure that the arm ends up in the 9 o'clock position when the power is applied to the Arduino. Now we will take the right servo motor to attach it to the right arm servo plate. Again, use one of the servo collars and note the orientation of the wire. As before, the servo collar is attached to the plate using 2 of the 8mm screws. Tighten the screws so that the motor is mounted firmly, but again, don't over-tighten them. Next, we'll attach the right arm base to the right servo motor arm using 2 of the screws provided with the servo motors. Tighten these securely. Now we're going to take the parallel linkage and attach it to the right arm servo plate using a 6mm screw. Fasten this down, but don't over-tighten it as it needs to be able to pivot. Next, we'll take the right arm base and attach it to the servo motor using the machine screw provided in the servo motor kit. We'll need a small Phillips screwdriver to perform this. Now we're going to assemble a component that's amusingly called the pig. Take the short servo arm, the left arm base joint, and the left arm mount tablet and fasten them together using a 10mm screw as illustrated here. Tighten the screw, but don't over-tighten it as the pig needs to be able to move. Now we'll take the servo arm to the base motor and attach it to the arm bottom plate. Once again, we'll use 2 of the self-tapping Phillips screws that are included with the servo arm kits. When we're done, we'll insert the machine screw in the center for use later. The next step is to insert the front arm base cross member. We'll do this with a 12mm screw and a nut, which we'll first insert into the left servo plate. We'll then install the base plate. Notice the notch in the plate for the nut. This will be difficult to maneuver, but once you get the nut into the correct position, tighten the screw to secure the member. Don't over-tighten it. The next step is to take our pig and insert it into the front arm base cross member, along with a parallel linkage and a small spacer. This is all held together with a 12mm screw. Tighten the screw, but don't over-tighten it, as this mechanism needs to be able to move. The next step step is to insert the bottom plate into the left arm plate and into the base of the pig. There are a number of notches in all of the pieces that need to be hooked up in order to make this work. Personally, I found this step to be a bit difficult, but with a bit of perseverance, you'll eventually get all of the pieces to fit.